Welcome back everyone. In the last lecture we had done a recap of everything that we had studied till now about root locus. We took all the time domain specifications, we looked into everything, we brought everything together and we saw what is the interpretation, how can we graphically understand how does the closed loop pole locations affect the different specifications. Today what we will do is we will take examples, okay, we will take examples and try to design controllers. We will try to specifically meet the specifications that are given to us using the root locus. Let us go ahead and do that. Here is our first problem statement. The problem statement says that the open loop transfer function OLTF here is short form for open loop transfer function. Okay. So, this is the short form for OLTF is open loop transfer function, CLTF is closed loop transfer function. Okay, I will be using it quite often. So, hence I am just telling you what the abbreviation stands for. So, now the open loop transfer function of a unity negative feedback system is given by this. So, as soon as this is said, you should understand that okay, the system what is the open loop transfer function? Remember, the open loop transfer function is GS into HS, right. If you remember, now in this case HS is equal to 1 and GS is equal to this. Okay. Now, same problem could have been drawn in a different way also. This you could have drawn as 1 by S plus 2 and this could have been 1 by S plus 4. Then also the open loop transfer function is 1 by S plus 2 into S plus 4. Okay. But I mean does not matter because we are only concerned about G into H. In this case G into H is 1 by S plus 2 into S plus 4. Here since it is said unity negative configuration, we know that H is 1. So, GS must be this expression. Okay. So, the open loop transfer function is given to us. The question is determine the value of k. So, k here is a positive value from 0 to infinity. Okay. We have to determine the value of k so that we attain 40% overshoot for unit step input. So, if I give a unit step input here, I should attain 40% overshoot. Okay. Again remember in the last class itself I have said user might not give you the specification in this nice percentage overshoot form. You will have to come up, you will have to understand what the user requires and have to reformulate the problem in the specifications that we deal with. So, 40% overshoot is what we need. Okay. So, now let us, so the first step in any design problem is first try to design controller design problem is first try to find out the desired pole locations. Okay. What will be the pole locations that gives you this 40% overshoot? First that should be your aim. Okay. So, once you get to that, then you proceed forward as to which procedure you will use. Now, we are learning about these controllers where we are just using constant gain blocks here. Later on we will see that we will replace those with different other transfer functions, but for now we are just learning this. But in most of the cases the base idea is that first you have to come up with the desired pole location. Okay. So, let us come up with the desired pole location first. Now, so by this information as soon as someone says that oh we have 40% overshoot, then you know that we have an overshoot formula, you can directly use that. By the way, one more important thing. First of all, look at this system and see whenever you have a problem, try to get the intuition of the problem first. Okay, fine. We have a problem here. You see in this case we know that the open loop transfer function is a second order system in the sense that the denominator has 2 poles in this, right. Now, if you would have write down the closed loop transfer function, you do not have to do it here, but I am just giving just trying to explain a point. So, here what will be the closed loop transfer function? It will be Ys by Rs, right, and which will be coming out to be k by S plus 2 whole into S plus 4 by 1 plus k by S plus 2 whole into S plus 4. So, as a whole this is k by S plus 2 whole into S plus 4 plus k. So, this is the closed loop transfer function. You do not have to write it down actually, I mean just I am trying to make a point here. So, the point here is that you see the closed loop transfer function, how many poles will it have? It will have 2 poles, right. So, since it will have 2 poles, we can directly use the formulas. Even with 3 poles we will be able to use the formulas, but then in that case we will have to keep in mind some approximation thing also. But for now we know that okay, this is a system which will have two closed loop poles, so fine, I will directly use the formulas. Okay. So, I do not have to think much in this case. So, let us just go ahead and write down the formula. So, what is the overshoot formula? So, MP equal to 40%, we know that the formula for overshoot is e to the power of pi zeta by root over 1 minus zeta square. You go ahead and solve it, you will get zeta equal to 0.28. Okay. Now, in some cases I have seen over the years, I mean people make mistake while solving this, is E, right. So, you have to take ln, not log, remember that. Okay. So, zeta equal to 0.28, fine. Remember in case of Bode plot when we had discussed, that was log 10, the base was 10. In this case this is ln that we are talking about. Okay. So, keep always remember, I mean all these things, these are subtle things, but these are the things which where you make mistakes and then you will keep on scratching your head as to how do I solve the problem. Okay. So, always remember these subtleties. Okay. Now, here we have zeta equal to 0.28. Okay. So, if zeta equal to 0.28, we know what is the formula for a second order systems closed loop poles. We know the closed loop poles are given by this, right. So, if these are the closed loop poles, so in that case, so we will have zeta equal to 0.28 and this will be the form we will have. You see here we had one specifications and we could only get the value of zeta, we do not know what is the value of omega n, okay, and that is why we will have to figure out, fine. So, this is the desired pole location. Of course, we did not get a clear desired pole location because this pole location depends on the value of omega n. Okay. Now, let us see if I draw the root locus, can I get some idea. So, if you go ahead and draw the root locus for this, how will you draw the root locus? To draw the root locus, you will have to write down the open loop transfer function. In this case, the open loop transfer function this itself, because h is 1. So, for this transfer function, you will have to draw the root locus, right. And if you draw the root locus, you use, I mean as a practice, why do not you try to use all the steps that we had followed while drawing the root locus, and see whether you get a root locus of this form. So, yeah, these were the desired pole locations. So, the root locus will come out to be of this form. You can see that there is an open loop pole at -2 and -4, and the root locus will start from these points. Then there will be a breakaway point somewhere here. Okay. The value is -3. You use the breakaway point dk ds equal to 0 idea, you will find it to be -3, and then the two branches will go off to plus infinity and minus infinity, because there are no finite zeros here where the branches can terminate, right. So, both of them has to move to plus infinity and minus infinity, and this is how the root locus will look like. I urge you to find out this root locus on your own. Okay. I mean on MATLAB you can directly find out using a command rlocus. Okay. Use rlocus bracket, within the bracket you give the transfer function, you will get the root locus. But of course, you can draw it directly from MATLAB, but you should understand what it means. So, better you first go ahead with all the points that are given to you, you try to draw the root locus on your own, you will get the intuition. Okay. The software can always do that, but once you get the intuition, it will become helpful. You will see how the intuitions will help. Now, you see, now for this root locus I need zeta equal to 0.28, but I know on the complex plane, how do I get to 0.28? You know that zeta equal to 0.28 is just a line, right, it's just a line like this which will go from origin, right. And so, if you find out the angle, what will be the angle? The angle will be 73.7 degree, because zeta is cos phi, you go ahead find out phi equal to 73.7 degree, and if you draw a line which makes 73.7 degree with the negative side of the real axis, then you see this line will cut this root locus at this point. So, this point becomes your desired pole location. Why this is the desired pole location? You see, this is the desired pole location because what is root locus at the end of the day? Root locus was the collection of all the closed loop pole locations when you vary the value of k from 0 to infinity, right. So, in this plot, when you are seeing this root locus plot, you are basically looking into, in this root locus plot, you have collection of all the closed loop poles. If you have the collection of all the closed loop poles, the only thing that now you have to figure out is that, okay, on which of this point will I have zeta equal to 0.28. But I know that because I can easily find that, because I know that if the zeta equal to 0.28 line cuts the root locus, that is the exact point where you will have zeta equal to 0.28. Not here, but here at this point, because at this point the zeta equal to 0.28 line cuts the root locus. Great. Now, once I know that, now look at the root locus. Okay, you look at the root locus and the desired pole location. So, the desired pole location is at this point, but at this point what is the real part? The real part is minus 3, right. So, that means this part must be equal to minus 3, right, because this is the desired pole location and the desired pole location's real part is coming out to be minus 3. Okay. So, therefore, minus 0.28 omega n equal to minus 3, and from there omega n will be coming out to be 10.7143. So, once you know omega n, you can find out the exact desired pole location. So, the exact desired pole location will come out to be minus 3 plus minus j 10.2857. Remember, this will have the complex conjugate also. If this is a desired pole location, the complex conjugate also will be a desired pole location, right, because you remember the root locus therefore is symmetric, right. If this is a point, then this will also be a closed loop pole location. Fine, great. So, we have the desired pole location now. So, but what was our idea? I mean, fine, we found out the desired pole location, but our idea is to find out the value of k. I need the value of k which will lead to this desired pole location. Again, let me just re-emphasize, what is the root locus? The root locus is the collection of closed loop poles when I change this value of k from 0 to infinity. So, at k equal to 0, I am at this point, at k equal to 1, say I am at this point, at k equal to 2, I am at this point. So, I am at this point means the closed loop pole locations are these. Okay. So, in this way, similarly at this point there will be a value of k. Now, what is the value of k at that point? If I find out the value of k at that point, I have the value, I have the controller, right. So, let us try to find out the value of k at that point. Now, how will you find out the value of k at that point? Again, let us go back to the basics of root locus. How did we draw the root locus? Root locus was drawn using two criteria. One was the angle criteria, remember the angle criteria, and the other was magnitude criteria. Okay. Now, what did the magnitude criteria tell us? The magnitude criteria told us that k of g s into h s must be equal to 1 at the point where at the point on the root locus. So, any point on the root locus must satisfy this. So, that means this point we must also satisfy this. If this point must satisfy this, then at the point minus 3 plus j 10.2857 I must have this equation satisfied. Now, g into h I already know, g into h is this, right. So, only thing is that I have to find out the value of k, and that is what we are going to do. You see, k by s plus 2 s plus 4, at the point I am evaluating it, you just plug in this value here. So, these are the complex numbers you get. You see, we are talking only about magnitude, right. So, magnitude of the left hand side here of this part is nothing but this, right, and from here I can find out the value of k. Again check again. So, this is the magnitude of this part. You can just do a real part square plus imaginary part square root, you get the value of k simply comes out to be 106.7956. So, this means that at this point the value of k is 106.7956. So, you can put that value, that will be your closed loop location. Since this is the closed loop pole location, the complex conjugate will also be the other closed loop pole location. You found out for this, but its complex conjugate will also be, because they are moving together in symmetry, right. So, if k value is at k equal to 106, if you are here at k equal to 106, the other branch is at this point. Okay. So, let us see does this work or not. So, here was our desired pole locations. So, this is the value of k that you had, and now in MATLAB we can directly see whether it works or not. So, first of all I will write down the transfer function. So, you know how to write down transfer function already. So, the open loop transfer function g is this, then the value of k I have written, and now comes the closed loop transfer function. Remember, this I had already talked about earlier. So, what is the syntax of closed loop transfer function? So, closed loop transfer function is, see, this is what? This is k, this is g, and this is h. So, if you use the command feedback, so in feedback in feedback you have to give the open loop transfer function here, which is k. If I take the k together, so this is k g into h comma 1. 1 means negative feedback configuration. If you give -1, it will be the positive feedback configuration. So, this command gives you the closed loop transfer function. What is the closed loop transfer function? K, in this case k g by 1 plus k g. This was the closed loop. So, this directly you can compute using this command. You do not have to go ahead and write down this expression. Okay. Why am I writing this command? Because at the end of the day, this entire system is nothing but kgs by 1 plus kgs. This is the closed loop transfer function, CLTF. Okay. So, the closed loop transfer functions once I have to this system, I can give unit step input and check what is the output and see if the overshoot is correct or not. Okay. So, that is the reason I am finding the closed loop transfer function. Further, using the closed loop transfer function, I can also find out what are the closed loop pole locations, because I just have to look at the pole locations of this transfer function. So, we will use that as well. So, I have defined the closed loop transfer function. So, once I have defined the closed loop transfer function, now I will find out the pole locations. So, this is the command for pole locations. So, what is the command? So, it says PZ map. PZ map is pole 0 map of close underscore loop. Close underscore loop was the closed loop pole transfer function. So, I am finding the pole 0 map of the closed loop transfer function and I am saving it into p comma z. You can give other variable name also. The first variable here is poles and the second variable here is zeros. Okay. So, let us see what are the values of p and z. So, you see p is this and z is this. So, that means with this k equal to this, the closed loop pole locations are this. Okay. So, if these are the closed loop pole locations, so if these are the closed loop pole locations, you see this is matching, right. This is where I wanted the closed loop pole locations to be and exactly I am getting that. Now, I find out the step response. Now, in the step response, you see the peak part comes out to be 40, right. Again, let me just quickly go ahead and repeat this. See, here the closed loop pole locations were this and there were no zeros in this case. Then I find out the step response using the command step. So, step within bracket, if you give the closed loop pole location, this we have seen earlier how to find out these responses. I am just repeating again how to find out step response. Now, you see once you have the step response and you right click, you will find out in the right click option. So, let me just go back again to show you the option. See, if you right click on your mouse on the step response, you will have these characteristics: peak response, rise time, settling time, transient time, steady state. So, MATLAB will directly show you those. Okay. So, I wanted to only check the peak response because I want 40% overshoot, right. So, you see if I look at the peak response, you see the peak response overshoot is 40% and the time taken is 0.307. Okay. So, this is the peak time, 0.307 is the peak time and 40% is the overshoot and that is what we wanted, right. So, we have actually got what we wanted, fine. So, this basically in this problem we have solved the problem because this is what we wanted and this is what we got. Okay. Now, let us take another problem. Okay. Now, let us take another problem which is this. Okay. Now, what I have done is, now you see this is no longer a second order system, now I have added a S here. So, now this is a new problem where we have the open loop transfer function is a third order system. Okay. So, the question is a bit different now. In the previous case we were going for 40% overshoot, now I have changed the parameter. I have said that no, we want to go for a settling time of 8 seconds. Okay. Great. Now, the question arises, this is a third order system, can I use the formulas of second order system? It turns out yes, you can use the formulas for second order system, but we will have to be a bit careful. What is this carefulness about? We will talk about that when I will end solving this problem. Okay. So, first of all, let us blindfolded think that okay, this is a system, I want a settling time of 8 seconds. Okay, I know the formula of settling time of 8 settling time, I use the formula, I find out the desired pole locations. Okay. So, let us try to find out the desired pole location first. So, using that formula, what was the formula? 4 by zeta omega n equal to 8. So, zeta omega n comes out to be 0.5. So, that means my desired pole location now becomes minus 0.5 plus minus j omega d. In the previous example, omega n was not known. In this example, omega d is not known. Zeta omega n I know, okay, but omega d I specifically I do not know. So now let us look at the root locus of this. Again, you try to find out the root locus on your own. So here is the root locus. This is how the root locus will look like. You see, there is an open loop pole here. There is an open loop pole at this at -2, and then there is an open loop pole at -4. Okay. So there will be no root locus on this part of the real segment, right. So now this is the breakaway point at this point. So finally this is how it will look like. I urge you all again to go ahead and draw this. What is this exact point? What is this exact point? You can go ahead and draw. In some cases actually we do not even need all these exact points, okay. We just need an idea, and that is what we are trying to do here. So now I want my desired pole location to be -0.5. So I know, remember, the real part is this, right. So the settling time directly gives you the real part. So the real part has to be 0.5. So suppose this is 0.5. So you see this line, any point on this line will correspond to zeta equal to 0.5, and this line cuts the root locus at this point. So this is the point which will be your desired pole location. These 2 points will be your desired pole locations here. So since this is cutting at these points, that means I can reach to this point. There will be a particular value of k which will give me these points. So I just have to now figure out what is that value of k. Okay. I hope up to this it is clear. We found out the desired pole location, not exactly, but I know that the desired pole location now lies on the root locus. Once I know that the desired pole location lies on the root locus, I know that I can find out a value of k that will take me to that point. Now the question is, how do I find out the value of k? Can I use the magnitude criteria? Suppose I use the magnitude criteria directly. So what is the magnitude criteria? It says that k of gs hs equal to 1 at s equal to the desired pole location. This is what the magnitude criteria says. Now you see, the problem here is the desired pole location here is this, right, -0.5 plus minus j plus j omega d say. So if that is the point, now if I go ahead and plug this in this transfer function, this transfer function will become a function of omega d, because omega d is not known, and then there will be k which is not known. So I will have an equation which will have two unknowns, one is k and one is omega d, right. There can be infinitely many solutions that I can come up with, okay, but I do not need the infinitely many solutions. I need that exact solution where this line cuts the root locus. So what to do? So we know that there is another criteria, right. We do not have to go for a magnitude criteria in this case. I can go for the angle criteria. I know that this point, this desired point lies on the root locus. So if this desired point lies on the root locus, I know that that point must satisfy the angle criteria. What was the angle criteria? The angle criteria was that to this point I will draw these phasors, and the angle contribution from them at this point must be a odd multiple of pi, right. Any point, again repeating, any point on the root locus satisfies two criteria. One was the angle criteria, one was the magnitude criteria. Magnitude criteria I used in the last example, okay. In this example I am using the angle criteria, not the magnitude criteria, because the magnitude criteria is not helping us. The angle subtended from all the poles and open loop poles and zeros of the transfer function on the point on the root locus must be a odd multiple of pi, okay. Let us see whether this point helps us or not. At this point let us see what is the angle contribution. So if I find out the angle criteria using the angle criteria, so these will be the angles. You see what will be the angle here? See, again remember, all these three are poles, so they are the denominator, so which means there will be a negative sign coming, okay. So we look at the first term. So the first term here is, the magnitude here is 4 minus 0.5, and the magnitude on the imaginary part is omega d. So tan inverse of omega d by 4 minus 0.5. What will be the angle here? Tan inverse of omega d by 2 minus 0.5. What will be the angle here? It will be 180 degree minus the angle here. So pi minus tan inverse of omega d by, so this is 0.5, so omega d by 0.5. So the angle contributions I have written, and I know that these angle contributions must be an odd multiple of pi, Okay. Now, I have to choose something on the right hand side. Odd multiples means infinitely many odd multiples can be there, right. What should I choose? You can choose any one of them, you can choose any value of k equal to 0, 1, 2, whatever you want to, even negative also is fine. Okay. But what we will do, we will carefully choose it so that our expression becomes easier. Notice that if I open this bracket, then I will have a minus pi sitting over here. So, if on the right hand side I have a minus pi, they will cancel each other out and it will become helpful for me because one of the terms are gone. You can take something else also. So, what I did was I am taking minus pi here. You can try it with pi also on the right hand side, it is fine, you will get the same answer. So, once you try to solve this, the expression that will come out will be this, because this pi will cancel out with minus pi here and these terms I can take to the right hand side, and so finally I will be left with this kind of an expression. Okay. Now, how do I solve this? You know what is tan inverse of A plus tan inverse of B. I use the formula for that. So, I use the formula for that. So, this will be the tan inverse of A plus B by 1 minus AB, and on the right hand side you have tan inverse of omega d by 0.5. You equate all this, omega d gets cancelled, and then finally you are left with omega d equal to 1.6583. Great. So, I have found out the value of omega d. Now, I know the value of omega d, and that means this pole location is given by this, right. Now, once I have the desired pole location, now I know the desired pole location here. Once I have this location, now I have to just find out the value of k, and now I can use the magnitude criteria directly. So, the magnitude criteria will be k by this evaluated at s equal to the desired pole location. This must come out to be 1, and you will see that if you solve this, finally your answer will come out to be k equal to 14.998, right. So, I have found out a value of k at which this problem should get solved. So, this will be my value of k. So, now let us look at MATLAB and see whether this works or not. I am doing the same steps that I did for the previous examples. So, up to this I have found out the closed loop pole locations. Again, k was this. So, I have correctly found that, and see the desired pole location in this case is this. Okay. This was the desired pole location, and you will see if you look at, if you go ahead and find out the closed loop poles, the closed loop poles will come out to be these. So, look at the closed loop poles. The closed loop poles came out to be these. There are no zeros. Okay. So, there will be 3 closed loop poles. Yes, there will be 3 closed loop poles, because you see this is a third order system, and if you find out the 1 plus k g h equal to 0, this will be a third order polynomial. So, you should have 3 closed loop poles. 2 closed loop poles we chose, right, the ones which intersected that zeta omega n line, right. So, these are the 2 desired closed loop poles we chose, but we know that this is a third order system. So, there must be another pole, right. So, where is the other pole? The other pole is at minus 5. You can see this, right. Now, here is the part where the approximation thing comes into action. Okay. So, now what we did was essentially we took those specifications and we found out the dominant poles, the 2 dominant poles. The 2 dominant poles were minus 0.5 plus minus j 1.6582 or 3. Okay. So, that were the dominant poles. I wanted to make them dominant, which means my third pole should be at least 10 times away from them. Okay. Now, look at the dominant poles. The dominant poles are at minus 0.5 this. So, what is 10 times of the real part, which is minus 5, right. So, it is exactly sitting at 10 times that. Okay. Did I choose this? No. This came on its own, because I have not taken any special care to make it minus 5. Okay. So, we are expecting that, see, now the closed loop system that you have got has a third pole 10 times away from the dominant poles, which means that the output should actually mimic this second order system with these 2 poles. Okay. That is how we discussed approximation. Let us see how the step response looks like. So, the step response is this, and if you look at the settling time, you see now we can look at the settling time directly. If you right click, since we are dealing with settling time in this case, so you can directly look at the settling time and you can see that the settling time is 7.99. What were we expecting? We were expecting a settling time of 8 seconds, but we are getting a settling time of 7.99, which is okay, right? I mean 0.01 seconds, some tolerance is always there. Why did it work? It worked because although see we placed only 2 poles, we only took care such that the value of k is such that these 2 poles are closed loop poles, but the third one we could not do anything. Now, how is this third one coming into picture? Notice again, what is the root locus? In the root locus I started at k equal to 0. So, at k equal to 0 all the 3 poles are at this point. This is the open loop poles actually. As I increase the value of k, suppose I am at this point. So, the value of k is suppose at this point is say example k equal to 5. So, the other branch also k equal to 5 will be at this point, okay, and in this branch also k equal to 5 will be at somewhere at this point. So, if I would have taken k equal to 5, these 3 would have been my closed loop pole locations. Now, at k equal to exactly at k equal to 14.998, at k equal to 14.998, I am at this point. Okay, at k equal to 14.998, I am at this point. So, at k equal to 14.998, this branch will also be will have some point, right. So, k equal to 14.998 will be this. So, it turns out that this is nothing but minus 5 or minus 5. Now, you see this part I could not do anything about, I had no control over this third pole, only thing that I took care of is this pole. Now, if by some means this would have come on the, instead of moving away it was moving towards this poles, it would have become a problem, okay. But in this case since, so this is called at the end you have to check whether second order approximation is valid or not. So, with this value of k, the closed loop pole locations comes out to be this. Since the third pole is 10 times away from the dominant poles or the desired pole locations, so second order approximation is valid in this case, okay. So, we can go ahead and say that okay, we have met our design objective. So, next example that we will take, we have a different objective, okay, and we will see whether we will be able to achieve that or not, or there will be some issues, but this we will do in the next lecture. Thank you.